Long before dinosaurs, our planet was a very different place. There were no trees, no forests, and hardly any life on land. Most life lived in the oceans. Then, about 445 million years ago, Earth went through a disaster so big that it nearly erased the ocean's breath. Scientists call it the Late Ordovician mass extinction. It came in two waves. First, the world froze. Then, when the ice melted, the oceans lost their oxygen. Many creatures died in both phases. By some measures, this disaster was as bad as any in Earth's history. Yet most people have never heard of it. The Ordovician period began around 485 million years ago. Sea levels were high. Shallow seas covered large parts of the continents. The climate was warm and humid. Land was still quiet, with only low mats of microbes and tiny moss-like plants. But the oceans were full of life. This time is known for a huge jump in diversity, called the Great Ordovician Biodiversification Event. Coral reefs spread wide. Sponges and bryozoans built complex structures. New predators evolved. Grazers and filter feeders multiplied. The oceans became busy, crowded, and alive in ways never seen before. Trilobites were everywhere. These armored arthropods came in many shapes and sizes. They crawled along the seafloor, sifted mud, or swam above it. They were so successful that more than 20,000 species are known across their long history. Their eyes were made of crystal lenses. Their bodies rolled up like pill bugs when threatened, but their success also made them a favorite food for many predators. Some of those predators were straight-shelled cephalopods called endocerids. Imagine a huge conical shell, like a long ice cream cone, with a squid-like animal inside. Tentacles reached forward. A strong beak bit down on prey. These cephalopods were likely top predators in many shallow seas. Some may have grown several meters long. They glided across reefs like living torpedoes, hunting trilobites and other shelly animals. Other hunters were eurypterids, also called sea scorpions. They were arthropods with spiked arms and paddle-like tails. Some were small and quick. Others grew large and powerful. They lived in lagoons and coastal waters, and probably ate fish, trilobites, and even other eurypterids. Their bodies were built for ambush and speed. There were also conodont animals, which looked like small eels with big eyes. They had tiny tooth elements in their mouths. These microscopic teeth are very common as fossils. The teeth were sharp and extremely fine. Conodonts swam through many layers of the ocean and fed on small animals and plankton. Their fossils help scientists tell the age of rocks and track changes in ancient seas. Even older lineages from the Cambrian still had a few members in the Ordovician. One of the most unusual was Aegirocassis, a large radiodont. Instead of hunting, it filtered plankton from the water with comb-like structures. It is a reminder that in ancient seas, there were many different ways to live, and filter-feeding giants have appeared more than once in Earth's history. The Ordovician sky may have been busier than usual. Around this time, a breakup in the asteroid belt sent lots of debris into the inner solar system. Layers rich in certain meteorites show that more space rocks were falling to Earth. Some scientists have even suggested that Earth might have had a faint ring of debris for a while. That idea is still debated and not proven, but it is likely that many meteors streaked across the sky. Even with the rocky fireworks above, life below the waves continued to grow in richness and complexity until the climate flipped. About 4 or 5 million years ago, the world shifted from warm to cold, quite suddenly in geologic terms. This glacial episode is called the Hirnantian glaciation. Ice sheets spread across the southern continents, which were grouped as Gondwana and had drifted over the South Pole. As ice grew, it locked up huge amounts of water. Sea levels fell, in some estimates, by 70 to 130 meters. Shallow seas drained away. Reefs were left exposed and died. Warm water ecosystems vanished from vast areas almost at once. This sudden cooling delivered the first blow. Many species depended on shallow sunlit waters. Those habitats shrank or disappeared. Coral reefs collapsed. Communities of trilobites, brachiopods, bryozoans, and echinoderms lost their homes. Meanwhile, deeper parts of the ocean changed in another way. As currents shifted and cold, dense water formed, many basins lost oxygen. In some places, the waters became anoxic, meaning they had little or no oxygen. In other places, they may have become eosinic, meaning they also contained toxic hydrogen sulfide. Most complex life cannot survive without oxygen. Bottom-dwelling animals suffocated. Plankton communities also changed or collapsed as the chemistry of the ocean shifted. Even top predators struggled. Straight-shelled cephalopods lost prey and hunting grounds. Some eurypterids disappeared. Survivors often became smaller. This pattern is common after mass extinctions and is known as the Lilliput effect. Smaller bodies need fewer resources and may cope better in harsh times. New cold-adapted communities formed for a while. Scientists call these survivors the Hirnantian fauna. Life did not just vanish, it also adapted. But the hard times were not over. The Ordovician Ice Age was very strong in key ways. It may have held more ice than anything seen in the recent ice ages humans know. Global temperatures dropped by several degrees. With sea levels so low, the geography of entire continents changed. Broad shelves that once supported rich marine life became dry plains. If you were standing at the shore, the waterline would have moved far away. Reefs would sit stranded on mudflats. For creatures that needed shallow tropical seas, the world suddenly became too small. Then the second blow came. The ice began to melt. When ice sheets fail, they can collapse quickly. Sea level rises, sometimes in pulses. Water floods the shelves again. Sunlight returns to higher latitudes. Nutrients trapped in ice and sediments wash into the sea. This can spark huge blooms of algae. At first, that might seem like a good sign, more food in the water. But when a bloom collapses, bacteria break down the dead algae and use up oxygen. This creates or worsens dead zones. Anoxia can spread across wide areas. The second pulse of extinction struck many of the species that had survived the cold, especially those adapted to the new icy conditions. Now they faced warm, stratified waters that were short on oxygen. Many of them died. By the end of this two-step disaster, the losses were immense. Estimates vary by study, but many suggest that around 80 to 85% of marine species died. By genera, about half were lost. Coral reefs collapsed across most regions. Bryozoans shrank in diversity. Brachiopods suffered heavy losses, and many survivors were smaller than before. Trilobites lost many families and never returned to their former glory. Graptolites, which were planktonic colonial animals, also crashed. Some top predators, like the straight-shelled endocerid cephalopods, lost their rule of the seas. They did not recover their old dominance. Not everything perished. Eurypterids held on to much of their diversity and later became key players in Silurian ecosystems. Echinoderms, such as crinoids and their relatives, were badly hit at first but rebounded quickly in some newly formed tropical shallows after the Ice Age. Conodont animals recovered over time and reached new peaks later. Jawless fish were set back, but later expanded in the Devonian, which is often called the Age of Fishes. Evolution does not stop. After the crisis, survivors spread into the empty spaces. How does this event compare to other famous extinctions? The asteroid that ended the non-avian dinosaurs 66 million years ago is the best known. It was dramatic and sudden. The Permian-Triassic extinction around 252 million years ago is called the Great Dying and is often considered the worst overall, wiping out the largest share of species. The Late Ordovician extinction stands with these giants. In some ways, it was worse than the dinosaur ending event, especially in the oceans. It may also have had very high kill rates at its peak. Recovery took a long time, at least several million years, and in some places perhaps up to 20. For those who lived through it, the world changed for good. How do scientists know all of this? The evidence is in the rocks and in the chemistry of ancient sediments. Glacial deposits show that ice sheets covered parts of many southern lands. Striations on bedrock record the scraping of moving ice. Dropstones, large rocks carried by ice and released into fine marine sediment, prove that icebergs drifted over ancient seas. Dark, organic rich shales point to oxygen waters in many basins. One key chemical signal is a global shift in carbon isotopes called the Hirnantian isotopic carbon excursion, the HICE. This shift matches the growth and melt of the ice sheets and the changes in the carbon cycle. Other clues include oxygen isotope changes, strontium ratios, and unusual spikes in mercury that may signal volcanic activity. Fossil layers show sudden changes in which species are present, how big they are, and how they lived. What caused the disaster? There is no single simple answer. Several processes likely worked together. The continents were arranged in a way that placed Gondwana over the South Pole. That made it easier for ice sheets to form and grow. At the same time, new mountains were rising in what is now eastern North America. During an event called the tectonic orogeny, freshly exposed rock reacts with carbon dioxide during weathering. This process pulls CO2 from the air. Less CO2 means less greenhouse warming, which encourages cooling. There are also more exotic ideas. Some researchers once proposed that a burst of gamma rays from a dying star might have hit Earth. A blast like that could damage the ozone layer and cool the planet. This idea is interesting, but there is no strong direct evidence for it, and most scientists do not consider it likely today. Another proposal is a very large ancient impact in Australia, now buried deep. The feature is called the Deniliquine multi-ring structure. If it is an impact crater, it would be huge. However, it is not yet confirmed, and its age is still being studied. Finally, some studies note the spike in meteorites and even speculate about a temporary ring of debris around Earth. The ring idea is not proven and remains a hypothesis. It is possible that extra dust and impacts added to the stress, but they probably were not the main drivers. When the climate flipped, it did. So in two steps. First came cooling and a major sea level drop. Habitats shrank. Reefs died. Some deep waters lost oxygen. Then came rapid warming as the ice melted and sea level rose. Nutrients flooded the seas. Algal blooms exploded and then collapsed. This used up oxygen and created dead zones. The two pulses hit different groups in different ways. Warm water? Species died during the freeze. Cold-adapted survivors died when the water warmed and lost oxygen. It was a trap that caught life from both sides. After the crisis, the Silurian period began. The seas came back over the shelves. New ecosystems formed. Eurypterids became important hunters in many lagoons and estuaries. Echinoderms rebuilt meadows on the seafloor. Corals and sponges slowly began to make reefs again. The small eel-like conodont animals returned to their patrols. Jawless fish explored more of the water column. Later, in the Devonian, fish would conquer many niches and grow into many forms. Extinctions end chapters, but they also set the stage for new ones. Why does this ancient story matter today? Because mass extinctions show how Earth systems can change fast when multiple forces push together. They show that both cooling and warming can be deadly. They show that oxygen in the ocean is critical for complex life. When oxygen drops, food webs break. They show that even rich, diverse ecosystems can fall quickly if the base is shaken. Today, human activity is warming the climate, adding nutrients to coastal waters, and changing ocean circulation in some places. Dead zones are growing in many modern seas. The Late Ordovician is a warning. Once feedbacks begin like blooms that lead to low oxygen, they can spread, and are hard to stop. The Late Ordovician mass extinction is not just a list of losses, it is a test of life's resilience. It shows that life can rebuild, but it also shows that the recovery can take millions of years. The survivors change the rules of the game. Some groups never regain their old dominance. Others rise to fill the open spaces. The world after an extinction is never the same as the one before. Picture an Ordovician reef, at its peak bright, noisy, and full of motion. Trilobites move in schools. Corals wave softly in the current. A giant cephalopod glides past, a shadow, with eyes. Then, picture that same place a short time later, cold, empty, and silent. The corals are dead. The trilobites are gone. The predator has nothing left to hunt. This is what the first pulse felt like. Now picture the water returning, warm and green with algae. Fish gasp near the surface. Invisible chemistry steals the breath from the sea. This is the second pulse. Together, they changed the course of life. In the end, the Late Ordovician mass extinction erased a vast share of marine life. It reset the oceans. It ended the reign of some ancient champions, and opened doors for others. It left clear marks in the rocks we can still read today's glacial scratches, buried stones, black shales, and sharp shifts in carbon. It is a powerful story about how Earth works, how fragile life can be, and how quickly things can change when the system tips. Most people know about the dinosaur-killing asteroid. Far fewer know about the ice and breathless seas of the Late Ordovician. But if you lived in those oceans, this would have been the worst extinction you ever knew. Now you have heard its story.